Hi everybody, this is the $1 million puzzle, Hadrons and Quantum Computers, why modern physics needs a new global mathematics. So we're going to look at a circle of ideas that starts with particle physics, looking at quarks and nuclei, over solid state physics, looking at correlated electrons, going to quantum computing, where superposition of states is important, looking at topology, homotopy theory, here it becomes more mathematical, geometric homotopy, where things come together, and then very briefly at the end some outlook on homotopy type theory, the most abstract formulation. That's the circle of ideas we're after. So we start with the standard model of particle physics. It says that besides electrons, matter, the ordinary matter you see around you, is made of quarks. That's the technical term. Here's the picture you may have all seen. If you zoom into matter with a large microscope, very large microscope in the end, you see crystal lattices. They consist of atoms at their vertices. These atoms in turn have nuclei that consist of protons and neutrons, and so the story goes, each of these hadrons, these protons and neutrons, consist of quarks, 3 in this case. This is a technical term, quark, for the constituent of these protons. So generally hadrons, like the proton, are thought to be bound states of these quarks. Now, popularizers say that this standard model is so good that it leaves no room for improvement. Here's Peter Voigt in 2006. The standard model is just too good. This is picked up in 2007 by Dosch in Exposition of Quantum Chromodynamics. More physicists are there who complain that the standard model is too good, he says. And more recently, just last year, here's Ethan Siegel, I think. As 2025 stands, the standard model still hasn't cracked. When will its foundations crack, is the question, the rhetorical question. It's just too good, that's the attitude. In particular, they say, these popularizers, that experiments do not find particles that have not already been predicted by the standard model. Here, for instance, Wired in 2016. Sorry folks, the LHC didn't find a new particle after all, which is referring to no new particle beyond the Higgs, which was famously found. Here more explicitly, in Science 2022, 10 years after the Higgs particle has been found, physicists face the nightmare of finding nothing else. Because the standard model is so good, it has explained everything. Nothing new can be found. And yet, if you actually go to the webpage of the Large Hadron Collider, the big experiment that is, or has been running for years, you find that unpredicted hadrons are found all the time. This is Patrick Koppenburg here. On the web, he's a scientist at Large Hadron Collider. He counts 79 at least new hadrons at the LHC since it was turned on in 2012. So on the vertical axis you see the total number, accumulated number of new particles that have been found, hadrons, and on the horizontal you see the years passing by. It's almost a linear curve, so it keeps going. In the accompanying text, Koppenburg is very polite. He says experimental guidance is needed, which is a polite form of saying theory essentially says nothing about these hadrons. It doesn't predict them by and large. It doesn't retrodict them by and large. So even those that have been found, people struggle with explaining the properties. They've just been measured. So experimental guidance is needed. Theory is. So how can this be? Moreover, elusive hadron properties are known to mess up so-called predictions of the standard model. Right by the nature of quantum physics, so-called loop corrections, even if you're looking at processes that do not manifestly involve hadrons, they still come in with some probability, and since you don't understand them, they screw up the actual predictions of the process that you're looking at. So here's an article highlighting hadronic form factors remain one of the primary sources of uncertainty in this case flavor observables, so some other observables. Taming hadronic uncertainties was the title of that conference, but this was the talk. Tangents remain. So tangents is the jargon here for discrepancies between theory and experiment, between predictions and actual measurements in the CERN career. Just this year, essentially all the uncertainty in a certain measurement, G-2, some anomalous magnetic moment, come from hadronic vacuum polarization, which are unknown. Hadronic uncertainties versus new physics. So the trouble is that you cannot distinguish whether something is is some physical phenomenon beyond the standard model or just a hadronic uncertainty, because they're not known. So what gives? How can this be? On the one hand, people claim the standard model is too good to be true almost. On the other hand, it leaves these glaring gaps that we've just seen. Well, it's a public secret that these quarks we mentioned are actually a peculiar theory. Namely, individual quarks are not actually meant to exist. This is an idealization. They don't actually exist in the usual sense of existing. only quarks bound in hadrons are meant to exist, but, and that's the punchline here, the key, but the way they're bound is not actually explained by the theory. So the attitude in particle physics facing this situation is that the Standard Model explains hadrons in principle, but in practice it barely does. So that's how it goes. That's why you can have this attitude that the Standard Model is just too good, as long as you assume that in principle it would explain what it actually does not. Instead, people use various rules of thumb. The technical term is effective field theories, or models actually. So here's a list of them. The terms don't really matter. It's just what matters here is there's a lot of them. Chiral perturbation theory, constituent quark model, Namba-Iona-Laziano model, heavy quark effective theory, the square model, that's actually a good one. QCD sum rules, the bag model, holographic QCD, also a good one. And it keeps going actually. So all these are theories that are not actually derived from the Standard Model. They are little crutches that have been made up to explain us aspects of the world we see. But they're somehow, tacitly being subsumed as somehow being about what the Standard Model in principle explains. So you see, the situation is actually not really that of rigorous science that you would expect in the 21st century. This is not entirely unlike alchemy. The elephant in the room, of course, that causes this issue is that hadrons are what's called non-perturbative effects. It means they are not just small perturbations of the vacuum. They are not perturbations. So here's a cartoon picture to illustrate this. Imagine the vacuum in space, the vacuum of the world is a rope. I mean, that's a kind of that's an analogy, of course. So then a small excitation of this is, for instance, a little wave that can run through this rope. But a non-perturbative excitation, something like a knot, you cannot create such a knot by just perturbing the rope a little. You have to actually cut it. If the ends are tight, you have to cut it, make the knot, and tie it again. So it turns out these hadrons, in a precise sense that we will get to a little bit more, are actually more like these knots. But the formalism that people have, the 20th century quantum field theory, that was predominantly perturbative. It predominantly concerned only these perturbative excitations. It had nothing, or next to nothing, to say about these non-perturbative, knot-like excitations. So in fact, the quantum field theory that is praised so much as explaining everything and being the most precise theory that mankind has ever come up with only sees an infinitesimal neighborhood in the space of all quantum phenomena. So here's a cartoon. Quantum phenomena or quantum field theories are parameterized by two parameters. One is called Planck's constant, that measures, its size measures like how quantum a phenomenon is, how non-classical. We'll come to this later. And the other is the coupling constant, that measures how strong things are interacting with each other. And in a precise sense, turns out that perturbative quantum field theory, the method that is actually known, only concerns the neighborhood of the origin of this plane here, of this space, where these two parameters are zero, the neighborhood of that. In fact, it's in a technical sense, technically precise sense, the infinitesimal neighborhood. So this vast realm of finite Planck constant and finite coupling constant is the non-perturbative realm. It's everything, essentially, except this infinitesimal point that lies largely unexplored. And that's where hadrons are known to actually materialize in their natural properties. So there's something called the Clay Math Institute, an institute concerned with promoting mathematics, has declared in 2000 the non-perturbative formulation, the outstanding one, of hadrons to be a millennium problem of mathematics. And they offer $1 million prize money for solving this problem, for giving actual proof of the confinement, as one says, of hadrons, of quarks inside hadrons. Now, while the proof of quark confinement in hadrons remains wide open, that's why the prize money is there, a suggestive heuristic picture has actually solidified over the decades. So people have a physics picture of what should be going on, which has not been made precise yet. Namely, the idea is that there are what's called color flux lines between the quarks. They're compressed to a flux tube or string, that's the string of string theory actually, which binds them together. So here's the cartoon picture. So imagine there's two quarks. We want to explain why are they bound to each other in a hadron, in this case called a meson, because it just consists of a quark and an antiquark. And the idea is, well, like poles of a magnet, to which will come, they emit these flux lines, but they're compressed to actually form a narrow tube or string of flux between them. And as you try to move these quarks away from each other, that string will have to stretch, but it has a tension and keeps these quarks together. That is the heuristic picture of what keeps quarks together. In fact, it goes on, it says this compression of the flux lines to a tube is caused by what's called a condensate of magnetic monopoles. I have a cartoon for that. It's maybe not too important, but maybe for later keep in mind the term magnetic monopole. So one imagines actually the whole vacuum is filled with what's shown as little balls here with what's called magnetic monopoles, and by something called the dual Meissner effect, they cause this compression. So that is the physics picture. The question is then how to make this mathematically precise, and that is currently a wide open problem, but we will get to this. We come to this later. Now first to a related problem. Namely, analogous issues actually haunt what's called condensed matter theory. That's what's called solid state physics. That's where many particles condense to solids and fluids. So that's the physics of the stuff of everyday life that actually surrounds us. So here non-perturbative strong interactions are referred to as strong correlations. It's just a different kind of jargon. So here's a cartoon picture of this. On the left you see weakly coupled electrons. So there's a bunch of electrons here, these little balls. And it's a surprisingly good approximation, even though they have this Coulomb interaction. They electrically repel each other. It's a surprisingly good approximation in many applications, for instance for the description of ordinary metals, to behave as if these electrons do not actually interact very much with each other. But of course in reality they do. And in some situations this matters, and then we speak of strongly coupled electrons, where they are tightly pushed together, so that if you move one of these electrons, everything else has to move too. So like in a mosh pit, I'm saying here, if you know what a mosh pit is, that's actually a quite fun analogy for strongly coupled electrons. So that's the analog of strongly coupled phenomena, non-perturbative phenomena in particle physics. So strongly correlated electrons show remarkable but largely mysterious behavior. Here's an article which says it explicitly, the strong correlations puzzle. And funnily enough, that article, that's from 2009, that proposes a resolution, but it's won by quantum simulation actually. So it highlights the resolution is not by theory. So that highlights again that theory is actually lagging behind here. You can see things in the laboratory that are not explained by theory. For instance, quantum Hall systems, that's what we're going to focus on a bit. These are 2D electron liquids in a transverse magnetic field. What does it mean? Here's a cartoon. Imagine, which you can do in interfaces between semiconductors, you can constrain electrons to essentially a surface, as indicated here. So imagine the electrons can no longer move in space freely, in 3D, but are bound to the surface. And at the same time, there's magnetic flux, magnetic field, transversely going through this plane in which the electron sits. The electrons interact by this Coulomb force that we mentioned, and there's in addition these magnetic flux lines. And imagine something remarkable happens when there are exactly k magnetic field lines per electron. So for the experts among you, by magnetic field line I really mean a magnetic flux quanta. We'll get to this. So if the magnetic field is so strong, it has to be really strong for this, or the electron density has to be tiny, that there are actually k magnetic field lines per electron. So here's a cartoon where we have on average 3 of these field lines per electron. So here's 3, here you see 4, but here's only 2, so on average it's 3. Then something special happens. This is called the situation of fractional quantum Hall systems. At filling fraction mu 1 over k. Namely, what is it that happens? Well, first notice that on such a backdrop, in such a state, in such a fractional quantum Hall state, if you have a surplus field line, so if on top of the ones that we already had, every 3 of them paired to 1 electron, suppose we have a surplus one here, which is not paired to an electron. Well, then conversely, that is from the point of view of the original state of the fractional quantum Hall state, this is like lacking 1/k of an electron, right? Because otherwise they were all paired this way. So these quasi-holes, they're called quasi-holes now because an electron is missing. So let's say physicists speak of a hole then, and they behave like fractional quasi-particles in the fractional quantum Hall liquid. So let's focus on 2 of these. And in order to draw what comes next, I'll remove all these arrows and just depict these 2 red arrows here by these crosses. This is a usual symbol for magnetic flux going through. Now it turns out as you move such quasi-holes around each other, as shown in the next picture, something most remarkable happens. If you braid the world lines, then this happens. So here's a cartoon. I hope you can see what I mean here. There were these quasi-holes here. Now you start moving them in time, vertically now runs time, and you make the world lines braid around each other, so just twist around each other in this form. Then it turns out the state of the system, called the quantum state, I'll say a bit more about this in a moment, changes by what's called a braiding phase. There's some complex number that gets picked up by this quantum state, and the key point is that this quantum state, this phase, depends only on the braiding and knotting. So it doesn't depend on how exactly you move these quasi-holes, but just on the fact that they wind around each other once or twice or n times. Otherwise, it's insensitive to the details of this process, and that is most remarkable. Now, these processes, such processes may surface what's called topological quantum gates. So imagine you can control this. This is the same kind of situation I'll shown horizontally. Suppose you can control in a controlled way that these quasi-holes braid around each other. Then you have a controlled way of turning quantum states into each other, and that can be used to model quantum computation. So in order to understand this, we need to step back, and I'll give a 1-minute crash course on quantum computing. So what's a quantum state? So as you zoom in with your microscope, turns out the states of nanoscopic matter are just probabilistic, and as such they are denoted by these enigmatic symbols, psi in H in Hilbert space. And a quantum gate is the controlled transformation of such quantum states. So if you have some way, from a controlled way, to turning these psis in a linear way into psi primes, that's a quantum gate. In analogy with classical logic gates, where you make classical states transform. A quantum circuit is an algorithmic combination of such quantum gates, so you just chain a bunch of them together, and then to quantum compute means to have a quantum circuit whose output is some predefined computation. So if you can arrange your quantum circuit so that you know how your state should transform, then actually doing that transformation means to compute that transform. So for certain tasks, one can show in theory on paper, quantum computers could be vastly more powerful than classical computers. That's why people are interested in them. Vastly more powerful. Well, in principle, you see, we have the same kind of in principle in high energy physics a while ago. No, it comes back to us. So the major hurdle, namely, for quantum computing is what's called the decay of the quantum state. The technical term is decoherence. So quantum computing gains its power from a phenomenon called quantum superposition. So quantum superposition means that in contrast to a classical situation where something is either in state psi or in state phi, the quantum system can actually be in superposition, can in some sense be in both states at the same time, or with some probability be in either state. In a coherent manner though. So in this kind of superposed state is what you need your system to be in order for these quantum transformations to have this extra power. But now it turns out that even the tiniest interaction with the environment, for instance just heat radiation indicated by these arrows here, just a heat bath, just the fact that your system is not at absolute zero temperature, already tends to destroy the superposition, to make these two superposed states actually become two separate classical states. So the power of quantum computing comes from superposition of quantum states. This is easily destroyed by interactions with the environment. So the currently dominant strategy towards future utility-scale quantum computers, in order to deal with this problem, goes by the technical term NISQ plus QUAC. So this means noisy intermediate scale quantum systems with quantum error correction. So the idea is the following. You do live with an unstable quantum memory that keeps decaying in milliseconds, but you try to keep it alive by continuously error correcting. Quantum error correcting is with a classical computer. So here's a cartoon picture. So you imagine you have a quantum computer, which is shown in the middle here. It's kept at some very low temperature, extremely low, some millikelvins above absolute zero. And then you have a classical computer that interacts with it and keeps trying to fix its mistakes. And if you work out the numbers, you actually need a classical supercomputer for that, for just the error correction. So which is already a bit funny, but it gets worse actually, because actually the classical supercomputer here is room temperature, whereas this thing is at millikelvin, so you cannot easily couple them. You will actually have to put your supercomputer in some way, or parts of it, at not quite millikelvin, but a few Kelvin temperature. And that actually requires technology, classical supercomputer technology that isn't even built yet. So the current picture of how to achieve quantum computation actually postulates that one first achieves currently unattainable classical computation, just in order to correct the errors of the quantum computer. So in short, quantum error correction is like continuously refilling leaking buckets. So after this technical picture, here's a cartoon picture, which I think captures the situation actually quite well, even though being a cartoon. So think of your quantum memory as being water in a bucket. You want to keep the water in there that is what you need in order to do quantum computation on. But now the bucket is actually leaky, it has lots of holes, water keeps escaping. So what you do is you build a contraption, a device, classical device, a very clever one, that tries to capture all this leaking water and fills it into the bucket. So you have this kind of messy situation where you scramble to refill the water. Well, I mean, this picture makes clear that more fundamental fix would be actually to plug the buckets. In this picture, it's very clear what you really want to do is get away with this contraption here, with this classical supercomputer error correcting your system, just plug the buckets. So that plugging of the buckets, this fundamental fix, is topological quantum. That's the technical term. This is an intrinsically stabilized quantum state by topology. So very much, or very analogous to these knotted states that hadrons are, which cannot unknot, not by small perturbations. You want to actually make your quantum states be such knotted states that do not actually decay, at least not by small perturbations. So it turns out the candidate platform for such topological stabilization are just those fractional quantum Hall liquids that we discussed earlier. Because, as I said before, for them, this braiding phase that kind of is the topological quantum gate only depends on the global braiding properties. So really on the knotted properties of these world lines, of these onions, and not on small fluctuations. So these technical terms, abelian braiding phases, have actually been observed. So this sounds like a very ambitious project, but they, in some minor form at least, these things have actually been observed. So in principle this seems to be possible. But many open questions remain. Theory is lagging behind, such as concerning the non-abelian, so the ones that are really needed, and the controlled way of braiding these. So it remains open how to actually use this in an actual quantum computer. In principle it seems to work, but many questions remain. So the question is how to actually understand non-perturbative physical fields. We've seen these two topics where it's crucial, or would be crucial, to understand non-perturbative physics, but it's not known. So how would one actually go about it? Well, at least a key aspect of it, a large part of it, is flux quantization. We're going to talk about a bit what that means now. Flux quantization implies a whole lot of keywords that you may have heard about that are count as non-perturbative effects. Solitons, monopoles, we've heard about monopoles, skyrmions, instantons, and so forth. So flux quantization is behind, and we'll indicate a little bit of how that works, behind at least a large number of non-perturbative phenomena. So we've written this encyclopedia article here on flux quantization, and what I'm indicating now is kind of a super short version of what it says in that article. So in 1852, Michael Faraday threw iron filings over the poles of a magnet. That was before the electromagnetic field was even known that it exists. And he observed this striking phenomenon that these iron filings arranged in these lines, now called magnetic field lines or flux lines. So this revealed magnetic field lines sourced or synced into magnetic monopoles. Here's another picture that illustrates this actually directly from his notebook, that indicates in this light color here how these flux lines go through imaginary spheres around the poles. So hence the magnetic field is encoded by how much flux there is through any surface element. Delta x1 times delta x2. So imagine, here's a cartoon picture. Imagine you have little surfaces in space, and here's a little surface element, and you have a rule called F2 here, which to every little surface element tells you what is the total magnetic flux going through it. That gives you an effective measure of the magnetic field. This assignment, F2, from little surface elements to how much magnetic flux there's through them, this is called a differential two-form in modern mathematical parlance. So magnetic flux density diverges at the monopole. We've seen, there's just a technical term of talking about the flux lines coming out of these magnetic poles, and it's divergence free elsewhere. Let's see, do I have the picture here? So if you had a monopole, just a single end of a magnet, then flux lines would be emanating from it, going through any sphere around it. But away from this pole, if you draw any other sphere away from it, then the total flux entering that sphere would always be the same as the flux leaving it. So it would be divergence free. So we can detect from how the flux goes whether there's pole sources. This is called the Gauss law, and this will be important. What follows? Technical symbols for this. That F2 is the magnetic field divergence free is D for divergence of the Riemann differential. dF2 equals 0. But in 1931, so that's what, 80 years later, famous physicist Paul Dirac noticed that there's more to the story. In this article, Quantum Singularities in the Electromagnetic Field, he points out that the total magnetic flux through any surface closed surface I should say, actually comes in discrete units, in integer multiples of a given quantum of flux. It's not arbitrary. It comes in discrete units. This is the most curious global constraint because locally the flux density is arbitrary. Could be anything. But globally, when you integrate that arbitrary number over any closed surface, it comes out in integer. Integer multiple of some unit. Well, that's remarkable. In the 1960s, 1963 on, 1967 on, I think, these flux quanta were actually seen and have ever since in what's called type 2 superconductors, so in certain materials, in the form of induced Abrikosov vortices in the electron current. So this is a chunk of superconductor, and if you turn on a magnetic field, it makes the electrons whirl around, and the magnetic field lines get compressed, and this is actually not a coincidence that we're again talking about compression of flux lines. This is what's behind this dual Meissner effect that we've seen before. Anyway, they get compressed and run through these vortices of electron currents called Abrikosov vortices, and there's exactly one of them per flux quantum. So it's an integer number of them. And now that's most interesting because it says, I'll just claim this now, I'll try to make it plausible, that mathematically this shows that the electromagnetic field actually has a classifying space. Let me try to make plausible what that means. So I ask you now to envision complex projective 2 space. You can't really do that. It's real 4-dimensional, it's hard to visualize this, but it's meant to be the space of complex lines, so of complex multiples of points in the complex 3 space, in the space whose coordinates are 3 complex numbers. So we can envision this for RP2. RP2 is essentially a sphere, but you just have to pretend now that every point you see here is actually has 3 complex numbers as coordinates. If you can pretend that, then the ambient 3 space we're seeing here is actually complex 3 space, and lines through the origin of complex 3 space are these complex lines, and the collection of all of them, indicated by this sphere-like thing here, is CP2, complex lines through the origin. So now it's just a fact of math, of algebraic topology, that this space, CP2, carries a universal flux density, lowercase f2, whose total flux through any 2 sphere is an integer. So there is an avatar flux density on this, kind of artificial space, which is not physical space. It's a classifying space, as we'll see, but it carries something that looks like a flux density and satisfies this funny constraint that Dirac said the electromagnetic flux should satisfy. So we can now, this is actually the avatar. From this, any other flux density can be induced. Space-time. It involves a classifying map to be called chi from space to this classifying space. So now on the left here, x3, think of this as being physical space, the space we inhabit. Think of it as Euclidean space for the time being, yeah? And here's this classifying space, CP2. And we envision we have a map that takes any point here to a point there. But being a continuous map, it also takes surfaces here. Here's a little surface element, as we've seen before, to surface element here. That's indicated by formulas here. And now since we have this avatar flux density over here, we can kind of measure how much hypothetical flux goes through this surface here. And then we can say, well, let that be the flux that actually went through this surface here. This is called the pullback of this differential form. And Dirac flux quantization says the actual flux density here should arise in this form by pulling back this universal one along classifying maps chi. So here it says again, on which the flux density F2 comes from the universal flux density lowercase f2. Excuse me. So this is the modern formulation of the electromagnetic field. And we'll say this in more detail in just a moment. Flux densities, F2, are part of the electromagnetic field, but actually equipped with these charge classifying maps chi and the compatibility condition, which I haven't really discussed yet and will not much, which says that chi actually reproduces F2 up to something called a gauge transformation. So the question is, what is the corresponding deformed effective description of surplus fractional quantum Hall flux? Right, we've seen that if we now have these flux quanta, which we've now understood for ordinary electromagnetism, for these effective surplus flux quanta on top of the strongly acting electron gas filled at this fractional filling level, so somehow apparently the flux quantization rule changes. And cleverly, as I've set it up, it changes in a kind of obvious way. We've had CP2 as a classifying space so far. Usually, I should say, for the experts among the the listeners here that, of course, in general, the classifying space is taken to be of the electromagnetic field to be CP infinity. But it was too hard for me to visualize and explain that. But as long as we're actually just mapping from just four-dimensional space-time, it's actually sufficient to map into CP2. So that saved me here. I could motivate CP2 a bit. And now, as we look at fractional quantum Hall flux, kind of the math actually, in a sense, becomes actually simpler. I mean, this is a bit misleading, of course. But it seems to become simpler, and that the classifying space looks simpler. It becomes CP1. CP1, if you think about it for a moment, well, yeah, maybe you have to think about it for a bit longer, but anyway, what I can find out is just the two-sphere, the ordinary sphere. Namely, the way this works now, the way that the two-sphere can be the classifying space for anionic flux is like this. Imagine again our plane here, which is this effectively two-dimensional surface that the electrons are constrained to. And then the surplus flux is, these little blobs around these anion core points, and imagine you wrap each of these little disks here around the classifying sphere, and map everything else to what's called the point at infinity, like the rear point of the sphere here. Then you get a map from that surface to the sphere, and that is the classifying map, or can be taken to be the classifying map of our surplus flux quanta. Surplus flux quanta get mapped around the two-sphere, and the world lines exhibit anion braiding phases. So the second sentence, it's not quite clear from the way I put it on the slide here, but the second sentence is a mathematical theorem that can be proven that if you have objects, points, that arise from such a classifying map to the two-sphere, then something called the Pontryagin theorem essentially implies, one has to work for this to show this, that the world lines of these pick up these braiding phases. So this is, here's the theorem. For surplus FKH flux, this classifying space gets C from to CP1. So this is the main result of this article we wrote, and we wrote in a bunch of other articles surrounding this theorem. Non-Lagrangian construction of anions and high-dimensional anions via co-homotopy. So this theory of classifying maps mapping to the two-sphere is known as co-homotopy. So here the anionic quantum states form local systems of Hilbert spaces over the covariantized mapping space. So I guess I'm jumping ahead a bit here, but in order to understand how such maps give rise to these braiding phases, one has to work a bit and realize that there's actually, for each classical background configuration of your system, indicated by this configuration space down here, for each of these points you have a Hilbert space of quantum states. So all possible quantum states form a space that is parameterized by the classical parameters. And as you move them around, which in our picture was would have been the movement of these loci of the onions around each other in this braiding process. So as you move them around in configuration space, the Hilbert spaces get mapped to each other by what's called unitary transformations, or called also the parallel transport with values and unitary operations along that path. You can also go in circles. So if you have a configuration here, and this is actually what a braid is. Remember, this is configuration space. Each point has a configuration of points in the plane. So as you move them around each other so that you get back to how they were originally configured, so that they've actually braided around each other once, then this unitary transformation goes from the given Hilbert space to itself. It's called a monodromy. And it's these monodromies that encode the non-trivial, what's sometimes called topological order of the quantum system. It's these transformations of the quantum states under movement of the external parameters, of which this braiding phase is an example. And if these transformations are topological and they depend only on the homotopy class of this path, then it means they're protected against noise and can serve as topological quantum gates. So besides rigorously rederiving the solitonic fractional quantum Hall anions, so rederiving the standard, more or less standard theory of these anions, turns out this new co-homotopical theory of anions via classifying space, via flux quantization, actually predicts non-abelian anions attached to superconducting islands in fractional quantum Hall liquids. Just as a side remark here, suppose in the fractional quantum Hall liquid you have a superconducting island, a bit that is superconducting. Turns out the magnetic field lines will be expelled from it, again by the Meissner effect. And these islands themselves, that's what this theory predicts, will actually serve as these non-abelian anions that I mentioned before are the ones that you would actually need for non-trivial topological quantum computation. So we published this in preprint, non-abelian anions attached to superconducting islands. Anyway, so, but remember we changed the classifying space of the electromagnetic field in order to effectively describe what happens in the vicinity of these fractional filling fractions. But but this also means that the Gauss law gets deformed. So remember, the ordinary Gauss law just meant that the flux density F2 of the magnetic field was divergenceless. Turns out, when you're operating now with a classifying space like the 2-sphere, when you change the CP2 to CP1, turns out there's another, mathematically at least, there's another flux density that appears, which however has a 3 form. So this is actually something that assigns stuff to surfaces. It's hard to, I will not try to give an intuitive picture of this. It's just the fact another kind of flux density, higher flux density appears, and it's not divergence free. Its divergence is actually the square, in some sense, the wedge square, as one says, of this flux density. So it turns out this is actually the Gauss law of another quantum field theory, namely something called a 5-dimensional Maxwell-Simons theory. So this is actually what one sees in hypothetical theories with more spatial dimensions than what we manifestly experience. And one can understand this theorem that I mentioned before by thinking of starting with a 5-dimensional quantum field theory, which is flux quantized using this classifying space S2, which is then dimensionally reduced to 3D Maxwell-Simons theory, and that one assumes that this 5D space actually has small curled up dimensions, say of the shape of a torus. Then one goes to the strong coupling limit to find this Simons theory, as it's called, that reproduces the phenomena we've just mentioned. So this is content of this article. So generally, higher dimensional fields in higher fields, like higher flux densities in higher dimensions, can be considered and have graded polynomial Gauss laws. So where an original Maxwell theory, Faraday-Maxwell theory, we have the single flux density F2, you can now imagine you have a whole sequence of them, F2, H3, maybe a 5 flux, and so forth. And the Gauss laws will in general say that the divergence of them are polynomial expressions, graded polynomial expressions, and the other flux densities, and some self-duality relation. So such Gauss laws are equivalently characterized by closed differential forms with coefficients in what's called the characteristic homotopy or infinity Lie algebra A. So that's a lot of jargon here that I have not and will not explain. The whole point is here that there's a symbol, this mathfrak A, which is an algebraic, mathematical, concise piece of datum, which actually exactly characterizes the solution spaces, characterizes these high magnetic fields. It's a little piece of algebra. Generally, higher fields and higher dimensions have graded polynomial Gauss law. Yeah. So this is the content of this article here. So there's something. So right, we said we need a classifying space in order to express flux quantization. So a character map associates such flux form data to classifying spaces. So it turns out there's the very general procedure where you start with a classifying space, you do something to it that mathematically is called rationalization. You end up with such a homotopy Lie or infinity Lie algebra, so you end up with a datum of Gauss laws, generalized Gauss laws for flux quanta. And this takes maps into the classifying space, so which we've seen characterizes the charges, generalized electromagnetic charges carried by the system, carries it to flux densities, called the character map. Because the flux densities, they lose a bit of information about these charges, but they're still characteristic of them. So hence global completion of a higher field theory by flux quantization is the non-perturbative completion, means to choose such a classifying space such that its image under this rationalization map is the given set of Gauss laws. So this is kind of this book we wrote, the character map in non-abelian cohomology. So the conclusion so far on fractional quantum Hall and outlook on the millennium problem is the following. We can understand the non-perturbative phenomena of the effective non-perturbative phenomena of fractional quantum Hall systems by starting with an effective fractional quantum Hall field theory regarded as a dimensional reduction of a higher dimensional field theory, a 5D Maxwell-Simons theory, and then pass to the global completion, to the non-perturbative version of that by flux quantization in 2 cohomotopy. Excuse me. By choosing a classifying space for that, in this case the 2-sphere. So, given the parallel between these two problems, one can then consider that something like this might work to address the millennium problem. So I'm not claiming that this has been worked out, but this is a plausible direction of attack, which has been proposed by other people. You could take your quantum chromodynamic fields, or the hadronic fields, and realize them as a dimensional reduction of some higher dimensional theory that looks like you maybe can say more about it. And there's actually a candidate for this called the M5 brain WSS model, Witten Sakai-Sakamoto model. And then you ask for the global completion of that. Turns out there's actually a good candidate for this, where this is flux furnace in 2 co-homotopy. This is a higher analog where actually the 3-sphere plays a role. And that's what really brought me into this topic. That's what we've worked on a bit, on the possible global completions of this M5 brain theory. So next we'll look more at the mathematical framework of this kind of setup. So we need to be speaking about non-perturbative phase spaces. We have seen that physical fields are encoded in 2 things. Locally, by flux densities satisfying Gauss laws that we expressed into this algebraic datum called the affine Lie algebra mathfrak A, encoded here. So flux densities are these closed forms of coefficients in A. And globally by charges within a classifying space, mathcal A, calligraphic A. So here's charges being maps to this classifying space. So the question is, the non-perturbative field content must combine these flux densities with these charges. But a priori, they live in completely different mathematical worlds. This is differential geometry here. This is homotopy theory. And traditionally, these do not talk to each other, have not talked to each other. But we can change this. We need to combine them. Gauge potentials should be the technical term for the thing, I haven't really explained this, that connects them, so that the global fields are objects that have as aspects of them flux densities and charges. So such a combination exists only, but it does exist in a novel universe of mathematics. It is what's called a homotopy pullback. So we can complete this to a square, certain information here, but then a homotopy pullback square in what's called a higher geometric topos. So I'm not explaining what this is here, but it is a universe of math where homotopy theory, topology of classifying spaces, can interact, and it gets unified with this infinitesimal structure of differential geometry. So this is the kind of book we wrote, the character map and non-abelian cohomology. Here's a summary of what we're doing here. So in passing to this geometric homotopy theory, this higher topos theory, claiming it's a combination of geometry, in our case differential geometry, and homotopy, the study of topological spaces and their deformations. Thus, to formulate non-perturbative physics has to happen in higher topoi. So even though higher topoi have a reputation of being involved, this is really a property only of what's called their set-theoretic models. Indeed, the abstract language of higher topoi, turns out, of course I haven't really shown this here, but I'm just telling you, is so neat that it even exists as a programming language. So you can even explain it to computers, to non-AI computers, just to dumb computers. And as such, it's called homotopy type theory, HOTT, hot. So it turns out in hot, all these basic ingredients of homotopy theory that we've been talking about have direct natural incarnations as computer theoretic things. So for instance, space, when you translate it to the homotopy type theory language, becomes nothing but a data type. A mapping space, so these things that we call map XA, becomes simply a function type, the data type of functions. This local system that are indicated is actually what encodes the topological order and the transformation properties of quantum states under external parameter changes like braidings, become what is called a dependent data type. So again, I'm not explaining this, but it's just the striking point here is there's just a form of data type in this programming language which encodes this braiding process. And then the parallel transport itself, that is the actual braiding process, is called type transport in homotopy type theory. So summary and outlook then, grand physics problem of the 21st century is the non-perturbative formulation of global physics. Highlighted one open problem, confined hydrodynamics, where unknown hadronic corrections infect all standard model processes and need to be understood before one can really claim that one understands particle physics. Second big open problem is strongly correlated electrons in solid state physics. And here a big motivation is that we need control over these topologically ordered states for meaningful quantum computing of the future. Now there's a tech strategy for both cases was embedded into high-dimensional high field theories, and the point of that was because then there's some good mathematical theory to globally complete these, to have a non-perturbative formulation by proper flux quantization. The necessary math for this is geometric homotopy theory, or the theory of higher topoi, which is a new form of global mathematics for non-perturbative physics. This is extremely rich in phenomena, but also extremely neat in the abstract. This is formal language, HOTT. So this is possibly the 21st century math for solving the millennium problem of physics. Possibly, of course, not claiming it has been solved. Slides and links and background material at this link here, ncatlab.org/Schreiber, that's my name, /show/Vico 2026. Thanks for your attention.